Hello, everyone. Thank you for joining today. I'm Haozhi Xiong, and this is my colleague Shiv Kushwah. We're here at the San Francisco Bay Area in California. When I was preparing for this talk, I started to think about subway a lot. Like everyone else, I travel quite a bit before work from home. So I've got a few tickets with me here today. BART, Metro, Oyster. Whenever I visit city, subway was a very convenient way to go around. If you look at the ticket closely, it never says who you are on it, but it'll for sure get you on the ride. So I've been wondering why we designed ticket that way and the benefit it gave all of us. Before I share more in today's talk, let me introduce myself real quick. So I'm a software engineer at Meta. I've been here for 5 years, and I'm currently working on privacy. Privacy is at the core of Meta engineering culture here. We have a global privacy infra team spanning across Menlo Park, Seattle, London, and New York City. Shiv will come back later today, and together we'll share our exciting story about de-identified authentication with you. We all know how the subway works. You buy ticket at a vending machine, insert your credit card, then you take ticket to pass the turnstile to get on the ride. You have to pass the turnstile because there is a cost to run the subway. It doesn't offer free rides. So there has to be the authentication step. Ticket here help us decouple the step of buying ticket and using ticket. While buying ticket needs to deal with various payment methods, interacting with bank can be time consuming. The use of ticket stays simple and efficient. We can offer rides to a huge number of people during rush hour. There is a greater benefit of this model, and that is privacy. The ticket doesn't mention who you are, while your credit card prints your name on it. The ticket very often doesn't do that. You're effectively receiving service in a more private way. The turnstile doesn't need to know who you are. It only needs to know that you're a rider that has already paid. We could have checked everyone's ID or credit card at the turnstiles too, but the amount of information collected will be more than needed to offer rides. Here, a privacy principle is we should minimize the amount of data where we don't need the data to provide service for a clearly defined purpose. Here with the subway example, life is telling us that we can provide some service without knowing your identity. Through the use of tickets, we de-identify all riders to a certain degree, and that is the privacy we all enjoy and deserve. Subway is a fairly large-scale public transit. You may not think the benefit is significant enough with just one city. But subway sometimes run across cities, considering all those crowded trains during rush hour throughout the United States and the whole world. The speed up and the privacy enhancements are huge. Meta also provides service at a global scale. There are 2.8 billion people using Meta products every day. We've created authentication systems like these subway tickets that also work at Meta scale. And it's been powering some of the key Meta services since last year. The best part is you don't need to buy a ticket and insert them. We've automated the process for everyone. We've also streamlined the process for engineers at Meta, so no expert crypto knowledge is needed to apply it to more products. In our mind, privacy is the default. Now, what is authentication? Authentication is the important step to know that you're a allowed customer. After authentication, the system will welcome you through the gate and guide you to a destination. What does it mean by de-identify? De-identify means we remove identifier about you or transform identifier in a way that cannot link back to you. So we only know you're one of the many authorized users. Authentication has been around for a really long time. Why do we upgrade it now? Privacy by design has been in Meta DNA. We always look for a way to improve user privacy. Meta also supports privacy mining regulation and the data minimization principle. One prime example of this wave of transition is to de-identify during authentication time. Next, Shiv is going to talk about how we leverage the advancement in academic research to enable authentication with privacy in mind. We bring this innovation to benefit everyone's experience.
Thanks for the quick introduction, Haozhi. Hi everyone, I'm Shiv Kushwah, and I've been working at Meta Privacy for almost 2 years now. Before that, I was at UC Berkeley, where I was involved in computer systems and security research. And that's honestly where I discovered my interest in working on cutting edge technologies and bridging the gap to make it more practical for industry applications. Now, as Haozhi mentioned, privacy is a core part of Meta DNA. We've always regarded data minimization as an important principle and have tackled challenges associated with it. Our earlier approach to kind of tackle this was by post-processing data in data warehouse. As you can imagine, this is computationally very expensive, and it's honestly pretty hard to determine on which data we can safely perform this operation in the first place. This was the case until we started work on our new generation of authentication in 2020. With our core value of privacy by design, we wondered if we could tackle this issue at its core and engineer a more scalable solution from the get-go. Fortunately, years of collaboration between industry and academia has yielded the anonymous credential, a technology we can leverage to accomplish our goals. Anonymous credentials support de-identified authentication by splitting authentication into two phases. To kind of briefly highlight how it works, if you take a look at the diagram, you can see the first phase, or what we call the token issuance phase. In this phase, clients contact us through an authenticated channel to send us a token, which we sign and send back. Then, in the de-identified authentication, or token redemption phase, clients then mutate this signed token they receive from us and use an anonymous channel to submit data. They authenticate using this token rather than user ID. While we simplified some of the nuances in the protocol, the key here is that the signed token and the redeemed token are unlinkable. This property enables the server to authenticate the client in the second phase without really knowing which specific client the token belongs to. Now, I skipped over some of the finer details earlier to give you the overall picture. In this slide, we'll be taking a deeper dive. For the full workflow, once again, we have a token issuance phase as well as a de-identified authentication phase. One item to note here is we actually also have a setup phase, where the mobile client obtains the server's public keys and other parameters. In the issuance phase, the mobile client creates a token and picks a blinding factor. It goes ahead and blinds this token and sends this blinded token to our servers, which sign this token and send it back. The client then unblinds this token and computes a shared secret, which is a function of the original token and the server's signature. Note that at this point, the server has actually never seen the value of the original token, only the blinded one. Later, in the de-identified authentication phase, the client forwards the original token, the business data, and an HMAC of the business data with the shared secret. The server can then essentially verify that the shared secret sent by the client is the same as the shared secret computed by our server by checking this HMAC. If this check passes, it's a legitimate request. I'll be passing the slides to Haozhi to discuss how we can leverage this technology in a meta service.
Thanks, Shiv. Now, how do we bring anonymous credential to reality? It makes sense from a research standpoint, but how can we use it to solve real problem at meta scale? So we've created a service with anonymous credential and called it ACS, Anonymous Credential Service. To see the architecture of ACS, let's grow a contrived application over Meta Infra. Let's call it real-time weather report. After all, weather can be a very valuable service to all of us. Let's begin with the open system. Any client can ask the server for weather reports. Without authentication, there is a lot of risk from malicious activity, such as scraping or DDoS. We can do better to protect our valuable service and make it available to people. So let's add authentication to the server. Now that the server authenticates clients, it is more secure. We won't spend resources on malicious actors, but instead we preserve them for legitimate users. The problem is that conventional authentication also brings in user identity. Common sense tells us that we only need shared geographic location to receive weather report. And identity shouldn't be required in the process. Let's improve the flow one more time. We've upgraded the flow with ACS now. ACS developed on top of Meta Container Framework. It provides API for credential creation and redemption. clients get anonymous credential in the authenticated channel, save them at a client-side storage. Then client use that anonymous credential in a de-identified channel to receive weather report. Remember that the property of anonymous credential is that a second round cannot link back to the original identity in the first round. So we've successfully provided authenticated weather report while we also successfully protected user privacy. It is a really nice win here. We've seen how ACS fit into this end-to-end scheme to improve privacy. ACS has several components embedded in the previous example. We need to enable engineers from all across Meta to use ACS without expert-level crypto knowledge. ACS has a client SDK to support client-side integration. And client can call high-level methods such as fetch credential that take care of contacting ACS API, blinding and unblinding data, and any other involved operation. Similarly, we need to make web layer integration easy with various product server logic. There is ACS library for a product to work with. In the end, there is backend service layer to maintain the root of trust. The service is in charge of signing. There's no need to call ACS directly if products use ACS SDK or server library properly. ACS backend service is a collection of hosts and shards spreading all over the world. It exposes a Thrift interface that allows creating and redeeming anonymous credential. Traffic is load balanced to all regions, and each region dynamically up or downside based on demand. But that's not all about ACS. ACS key store is in charge of key material. There are one security and one privacy consideration here. Firstly, ACS rotates its keys regularly. One way we do that is to leverage Kronos, Meta's async job infrastructure, and store key material in Meta's keychain service. It is a good security practice to rotate keys, so one compromised key won't keep the whole system in danger for too long. Secondly, ACS also publishes its public key for clients to fetch. ACS client has a chance to verify that the anonymous credential is indeed produced by the single public key announced. So ACS won't have a chance to identify clients with many client-specific public key. ACS also has a credential reuse detector, and it discourages credential reuse. In privacy, reusing credential increases the likelihood that multiple requests might be linked together. ACS detects reuse credential and fails authentication right there when the same credential has already been used a number of times before. That achieves the strongest privacy. It comes with an impact on performance though. The system needs to produce anonymous credential at a much higher rate when those credentials cannot be reused. There is a challenge to maintain good performance and privacy. So we've introduced anonymous credential service with our weather report application. It is a contrived example so far to help us understand what ACS design is. Next, let's see many real deployment in action. And Shiv, please keep me honest.
You bet. I'll be taking a moment to highlight some of the real-world use cases we're supporting. One of our major initial use cases was DIT, or de-identified data collection on WhatsApp. In order to provide the WhatsApp network at scale, we need to know how the service is functioning, which means we need logging. Before, we leveraged secure storage along with data deletion policies to ensure log data could never be associated with users. But we want to go further with our privacy protection measures, and that's kind of where ACS fits in. We created a system to enable WhatsApp clients to upload de-identified logs. Taking a look at the diagram, we can see that the mobile client first retrieves ACS tokens by authenticating via the existing WhatsApp auth mechanisms and receiving the appropriate ACS tokens in the response. These tokens are retrieved periodically and received in a batch. Then, when the client wants to upload its de-identified logs, it then contacts Meta servers through an unauthenticated endpoint, where it uploads the relevant log data as well as the ACS token. Our servers check the ACS token, and if the token redemption succeeds, then we allow the log data to actually be stored to our systems. This is a huge real-world use case, and the ACS server receives hundreds of thousands of requests per second from DIT. The next use case I would like to highlight is federated learning. As a quick refresher, federated learning is a technique where we are able to train a global machine learning model while keeping the actual private sensitive data on client devices. In this paradigm, devices share model updates with the server instead of raw sensitive data, and the servers compute the aggregated model updates and optimize the global model. Here's a possible avenue where we can leverage ACS to further preserve user privacy. We don't want malicious actors to send fraudulent model updates, but we do want to ensure that we allow legitimate users to help improve the global model. By leveraging ACS, we can ensure that the client model updates are sent in a de-identified manner by legitimate clients to further increase user privacy. Finally, I want to go over some key lessons we've learned through the process of ramping up our service to handle more and more use cases and a larger amount of traffic. As we were scaling up ACS, we noticed that we had to acquire new hosts and more server capacity on a 1-to-1 ratio with traffic newly onboarded. Given the recent supply chain crunch in servers worldwide, we started exploring how we could streamline ACS and make it more practical while still maintaining our high privacy bar. As Haozhi mentioned earlier, we decided to allow for use cases to specify a credential reuse limit within a reasonable threshold. On the ACS server, we added a credential reuse counter backed by ZippyDB, which is Meta's distributed key value store, that would count how many times a specific ACS token has been redeemed and fill the request if the token has been over-redeemed. Use cases that are inherently more sensitive have the option to set their limit of 1, which means no token reuse. However, other use cases can utilize a higher limit. By allowing for credential reuse, we're able to issue less tokens to service a particular use case, which enables us to save on server capacity. Another key lesson we learned was in regards to spiky traffic. Looking at some of our service dashboards, we noticed that there were small periods in the day when the ACS server received a large spike of requests, and our servers would actually be momentarily overwhelmed. As a result, there would be an increase in failed requests during this time period. We investigated further and noticed these spiky requests were actually just originating from 1 or 2 of our large use cases. After talking with the relevant client teams, we learned that their workflow was to cache data on the mobile client and batch upload at midnight. Now, although this is a great idea in theory, we learned that this model was effectively DDoSing our servers, as a bunch of requests came in at a particular time point. To address this problem for this particular use case, we added dithering to spread out the requests so that they weren't all sent at the exact same time. To solve this problem more generally, we worked with our traffic teams and added a global rate limiter that would selectively drop traffic headed to ACS servers if it exceeded a certain rate threshold to protect our server health. Now finally, another key problem we discovered while scaling up ACS was actually not related to the service, but on the engineering side. Initially, we only had a few engineers working on ACS. Between feature development and operational excellence, we found it increasingly hard to carve out time to onboard new use cases and support new teams using our product. At the time, onboarding new use cases usually entailed one of us working very closely with the partner team to explain key ACS concepts and even going through the process of manually provisioning a new ACS use case on our server. We decided to invest in a low-friction onboarding experience for new ACS use cases by creating a self-service onboarding portal in React. We additionally created ACS client SDKs in Android and iOS to provide quality crypto primitives and protocol implementations. Engineers can now call high-level methods on mobile, such as fetch credential, and these take care of contacting ACS service APIs, unbinding tokens, and any other involved operations. We finally revamped our onboarding wiki and invested in code gen tools. This further made it easier for clients to integrate with us while writing minimal code. These were all critical investments that enabled engineers from all across Meta to onboard onto ACS and let them use our protocols without having expert crypto knowledge. In the future, we want to guide Meta teams to leverage de-identified services to help transition towards privacy-aware infrastructure. To accomplish our vision, we want to make onboarding onto ACS even simpler and want to integrate even further with core infrastructure such as possibly Meta's graph infrastructure, allowing engineers to easily de-identify graph requests for first-party Meta services. De-identification is an essential tool, and we look forward to integrating de-identification with products beyond just authentication to preserve privacy and data use. At Meta, we're excited about the future of privacy. Cutting-edge technologies and engineering at scale will ensure we meet and exceed our privacy commitments for the time to come. Thank you.